This video looks at Objective 5 from Module 301D, Delta Systems. And it looks at what's called a 4-wire delta supply. The objective does not explain very well where this supply is used. And the idea of it is to allow us to supply 3-phase loads and single-phase loads from a delta supply. An ordinary 3-wire delta supply rarely feeds single-phase loads. Y systems are often used where we want to feed 3-phase and single-phase loads because a Y system can easily do that. A 12208 4-wire Y system can easily feed both single-phase and 3-phase loads. So to do the same in delta, we use what's called a 4-wire delta system. They're not used much now at all. They were used many, many years ago to feed systems where you generally had a lot of 3-phase loads, 3-phase motor loads, let's say, and you needed a little bit of single-phase supply as well. And the voltages of the system, as they show on this diagram, this is almost the most common voltages you would see in the field for a 4-wire delta supply. The phase or line voltage is 240 volts between A to B, B to C, and C to A. And the B to C phase is tapped in the center to give us a voltage from line B to the neutral of 120 volts or line C to the neutral of 120 volts. Okay, from there, there's a couple of code rules that we need to remember when we talk about 4-wire delta systems. And they look at these rules on the bottom of page 47. One thing to know is the rule you should look at in your code book is not 4-038 subrule 4. It is 4-032. Subrules 4 and 5. And those two rules, when you look them up in your code book, 4-032 subrule 4 states where the midpoint of one phase of a 4-wire delta connected secondary is grounded to supply lighting and similar loads. That is the neutral we're talking about here. The conductor will be color-coded white according to subrule 3, and the A phase insulated conductor is the conductor having the higher voltage to ground. So one thing we know about 4-wire delta systems as well is the B to neutral voltage and the C to neutral voltage are always the same, and the A to neutral voltage is going to be a higher value than B to neutral or C to neutral. So it is always called the high leg, and in Canada the A phase must always be the high leg. And then subrule 5 just talks about when we use this system to feed when we use this system to feed 3-phase loads and single-phase loads, one thing we have to remember is any panel that we use for 3-phase loads can only have line A, line B, and line C in it. It cannot have the neutral in a 3-phase panel because it is not a 3-phase neutral. It is a single-phase neutral. So 3-phase panels can only have lines A, B, and C in them, and single-phase panels can only have line B, line C, and the neutral in them. They are not to have line A in a single-phase panel. So that's subrule 5 just explains that as well. And other than seeing those couple little code rules and understanding a bit about where we use these systems, the rest of the objective talks about trying to calculate this high leg voltage and how you can use a phasor diagram and set up your voltages, and if you do them a specific way you can use your vector math, your horizontals, verticals to calculate what the high leg voltage is. And most of the questions you see on module tests will simply ask you about that high leg voltage, and I have a shortcut for doing that that hopefully will help you when you're doing questions like this. I'll show you a couple of examples. In this first example, it says the voltage produced by a delta connected transformer secondary is 480 volts line to line. So this is in this 4-wire delta secondary, we have a line voltage of 480 volts between A to B, between B to C, and between C to A. Our phase or line voltage is 480 volts. And it says if the B to C phase has a center tap, what is the voltage between that point and the high leg? So we know the voltage from B to the center tap is 240 volts. It'll be half that voltage. We know the voltage from C to that center tap is going to be 240 volts as well. And what we want to know is what is the voltage from A to that center tap? And that is what we call the high leg voltage. It is always a higher value than B to neutral or C to neutral. And I have a pretty simple way to calculate this value that you can use instead of trying to draw a phasor diagram and figure it out. I use a simple formula, and the formula is voltage of my high leg equals the phase voltage of the system times cosine of 30 degrees. It's really simple to use. So if I need to know what that high leg voltage is from A to neutral, I simply take the phase voltage that we have in the system, which is 480 volts, multiplied by the cosine of 30 degrees, which is 480 volts times 0.866. And that should give you 415.7 volts. So instead of doing a phasor drawing and trying to calculate where these voltages are at to do a vector sum of a couple different voltages, we can simply use this little formula and find out that our voltage A to neutral, or our high leg voltage, is 415.7 volts. And if I took a voltmeter and put it between A and the tap on the B to C phase, that's what I would read for a voltage. And that's one of the reasons that you would never want to have line A in a single phase panel. The single phase panel can only have B, C, and the neutral. If you had line A into that panel as well, every time you connected something to it, instead of getting 240 volts, which is what you would like, you'd get 415 volts. So it's not something you want to have in your single phase panel. Another example. In this question, we have a similar 4-wire delta connection where the B to C phase is tapped. The A phase always has to be the high leg according to a code. And it says the measured voltage from line A to the center tap in phase B to C is 300 volts. So the high leg voltage measured from A to that center point of B to C is 300 volts. And we want to find the phase voltage of this system if we know the high leg voltage. So again, we're going to use the same formula we used before, where voltage high leg equals V phase times cosine of 30 degrees. And we're just going to rearrange this formula. We know what the high leg voltage is. We're looking for the phase voltage. So V phase, to rearrange that formula, would equal V of the high leg divided by cosine of 30 degrees, which in this case equals 300 volts divided by cosine of 30 degrees. And that gives us 346.4 volts. So that is the phase voltage of this system, which means it's 346 volts on A to C, A to B, and B to C. 346.4 volts from A to B, 346.4 volts from B to C. So we can use this formula to figure out what our phase voltage is in a 4-wire delta as well. And that is pretty much the only questions, other than they could ask about the code. Otherwise, these are about the only kind of questions you'll see on 4-wire deltas. And this little formula should work well to figure them out and save you some work trying to figure it out with a phasor diagram. Hopefully this helps out.